Okay, thank you for attending in the PyData track. I'm talking about geodata processing using Python and JupyterHub. Actually, I made a typo. I wanted to write Jupyter Lab, and I ended up writing JupyterHub. But, but no problem, because I'm actually using JupyterHub for the same thing. So I will talk a little bit about JupyterHub too. The slides and also a Jupyter Notebook is available on GitHub. The link is here. I will also put the link on Slack, and I already posted on Twitter, so you can copy it later. So what is JupyterHub? JupyterHub is basically a server providing Jupyter Notebooks. Here is an example of a login screen. So I log in first, and then something like this shows up. I have a JupyterHub using Jupyter Lab. So I can choose different kernels. Here in this case I have Python 3 and R. And I will show during the talk we can also create our own kernels with specific modules on it. And then you can open your data, and all your Jupyter Notebook files are stored on the server. May I ask quickly the audience, who of you already used JupyterHub before? So not too many. So I can really recommend it if you have a setup and you have a good server, and that's the point. We recently got HPE Apollo 6500. It's extremely expensive, this server, running with 48 cores and 192 GB of RAM. And we also have 4 NVIDIA Tesla V100. It's the SXM2 version. It can be upgraded to 8 of these graphics cards, but for the first tests we only use 4. And we can do many things with that, especially deep learning, of course. And it's really, really fast. With over 5,000 CUDA cores per GPU, it's astonishing. The drawback, of course, you see it's 300 watts per GPU. So yeah, actually we are using the heat from the server to heat our building, so it's not that bad. So let me come to the main topic, processing geodata using open source modules. I call it open source modules. It's very important for me that it's open source. But what is geodata? Geographic data is defined in an ISO standard, the Technical Committee 211 series, and they do many documents. But the most important part is about 90% of government source data has a spatial information or a location component. So actually almost all data has location inside. And there are many geographic information systems, GIS, available today, and 2 are special because they support Python. One is the commercial ArcGIS from Esri, and the second is the open source QGIS. And you can create modules, you can program Python there, and you can do plugins or direct programming Python in that. But today we will not look at GIS software. Today we do everything in Jupyter Notebooks. So let me start. What kind of geospatial data I'm talking about? Usually I make 4 categories of geospatial data. We have vector data, you know that, for example, here we have footprints of buildings. We have raster data. Today we have, I'm from Switzerland, by the way, and in Switzerland we have at the moment 10 centimeter per pixel resolution orthophotos of the whole country. Another category are point clouds, and the 4th category would be 3D objects. However, I'm today only talking about vector and raster data. And basically there are 2 very important libraries for raster and vector data. One is GDAL OGR. GDAL is the Geospatial Data Abstraction Library created by Frank Warmerdam in early 2000s, and it supports many different formats. There is a Python binding, but the problem of the Python binding is it's really C++-like. So it's not really Pythonic, and for that Mapbox created a module called rasterio, which has a really Pythonic interface where you can read raster data. We'll look at that in an instant. For vector data processing, there is GEOS, Geometry Engine Open Source. It's a C++ library too. And there are also Pythonic bindings. The most important is Shapely. We will look at that in an instant too. And all together, Fiona Shapely built GeoPandas. GeoPandas is basically pandas with support of geographic information. So we will look at many modules today. I leave that slide. Let me first show you folium. Folium is a very easy to use module to just create a map. In basically 2 lines of code, okay, 3 lines if you count imports, you have a map. Behind the data we see OpenStreetMap, and we can make a center. That's actually here. We are in this building at the moment, and you see the location here specified and a zoom level. And now let's try to add some vector data to that map. Before I'm adding that, I have to tell you how vector data is defined. There are basically there are some standards like the OpenGIS Simple Feature Standard or the OGC the OpenGIS Simple Feature and the OGC Simple Feature Access Standard. And they define points, line strings, polygons, also polygons with holes, how they are done. There are many other things I'm not covering here, like circles or arcs and so on. And the interface is quite easy. With this well-known text, you just create a point and you make the coordinates inside. For example, point 1020, that defines a point in well-known text. Or you define a multi-polygon, that's 2 polygons. Also with this one, the first and the last are the same coordinates. It's closed always. And the second polygon we'll see first and last is the same too. So this one defines 2 polygons. And this well-known text can be used more or less directly in Python. Using Shapely, we import Shapely geometry and use the point and polygon or multi-point and so on, the different standards. And we can just create a polygon here with the coordinates. You can even display it immediately in the Jupyter Notebook and look at it. If you have it given as a string, like this point 1020 in a string inside, you can just use Shapely wkt load s, load string, and then you have the polygon inside. So I downloaded a polygon of Lithuania yesterday. I found one. I googled it actually and found one. I will show you after where you find these data sets. And then you can just load it from a file as GeoJSON. As a GeoJSON is a different format, also containing coordinates, polygons. It's the same principle, it's just a different syntax. So you have the polygon, multi-polygon, string, line string, and so on, and then its coordinates. And you can just read it and create a shape using Shapely and put it on a map, like folium. So you see in 4 lines of code, we can put this polygon inside. We just use folium GeoJSON and add it to the map. Okay, I will show that live later. So you saw some coordinates, but how are coordinates defined? And that's a really different case. Usually we use geographic coordinates. We have longitude and latitude. Latitude is the coordinate along the, let me say, y-axis, and the longitude is along the x-axis. And we see this so-called graticule on a sphere or projected, and this would look, if you look at a projected Earth, it would look like this. We see we try to reduce the problem from a 3D problem to a 2D problem, which also makes it easier. But on the other hand, we don't have a sphere. The Earth is not a sphere. The Earth is something like a potato. Yeah. And the problem is we have to approximate that. And if we take the sphere, we are really far off. We can, if you go to the next time to the airplane and they would take the sphere model, I think you would not arrive at the correct airport. You would be 60 meters at least wrong, and that's not good, obviously. So we approximate using an ellipsoid, and this ellipsoid was defined in 1984. So it's called WGS84. It's a world geodetic system, 1984, and the semi-minor axis from the pole to the center is this long, and the other one, semi-axis, is this long. So we can even calculate the flattening and many other things. I'm not going into details with these geodetic systems. We also have a second problem. We can project the Earth in many different ways. I just put 3 map projections here: Mercator, Eckert, Cassini. There are hundreds more projections, and that's something we have to look at. So there is a module called pyproj. Unfortunately, due to time reasons, we will not look into map projections too much today. But with this pyproj, we can really calculate, transform from one coordinate system to the other. And there are basically two very important systems. One is the geocentric Cartesian system. It's just a Cartesian system, X, Y, Z, where we have the Earth. But in general, if we do these visualizations, we use 2D, so we use a projected system. And this projection system, WGS84, is usually they take the EPSG code, it's the European Petroleum Survey Group. They have for every projection system a code, and the 4326 is for WGS86. So let's look at this example. We are located at this position, 5425. You see the problem? So what is 54? It's the latitude. So it's here, 54 up, yeah, and 25 would be around here. But you see what I did? I took the y coordinate first and then the x coordinate. That's a big problem. Usually some people say it's first latitude, then longitude. Other people say it's first longitude, then latitude. And we even have problems in some Python modules like Shapely, for example. In Shapely you should use the x, y thing and not the other around. So let me show that in a demo. Let me open the Jupyter Notebook. Let's go to the live things now. This Jupyter Notebook can be downloaded on GitHub if you want. Here are the installation instructions. I'm not going into it. Also here is an installation instruction if you want to create your own kernel just with these modules. So you can just, for example, change kernel and have your own kernels here. Okay, so let me test if I have the right kernel activated, and I do this folium. We see the map is just loaded, and in the center, that's at the moment the center of the world. We are located here. And you see again the coordinate. First is the latitude and then the longitude. So in folium, it's the lat-long convention. Okay, so let me make it a little bit bigger so you can see it from far behind. We can create polygon on the map. Let me first load this GeoJSON polygon from before with the JSON load string. And I can display it as a well-known text. You will see, if you know Lithuania, the border, there are not really many points. So it's really, really simplified. It's just for display reasons. After we'll have one which is much better. And I can display it on the map. You see, it's really just a couple of points. So if you zoom in, you see the borders really inaccurate here. But it doesn't matter, it's a principle at the moment. We see we can display polygons inside. Okay, so I create this a point of our location at the moment, and we see this is our location at the moment in geographic coordinates. Now Shapely has some binary operations, contains, intersects, within, touches, crosses, equals, and we can see, for example, if this PyCon LT, that's our position, is within the Lithuania polygon, and we see that's true. So we can really make a simple test here. You may have heard that EuroPython this year is in Basel, Switzerland. That's my hometown, so let me take the convention center there as point. And let me test if this EuroPython is within Lithuania, and you see, no, that's false. So it's in a different polygon. So it's really easy to use interface for really difficult tasks. If you program that yourself, you will see testing a point in a polygon is not just a couple of lines code. So another module is cartopy. As you saw, I use folium for displaying the map. With cartopy, you can also use maps and display it in different projections. And you see it uses matplotlib to display that. And if you have really a large amount of data, I recommend using this one map, so you can just plot all your data inside. You can also do some crazy things and change the projection type, for example, and have a map like this. I have more examples in the notebook. Let me do one last here, the Mercator Projection, known from Google Maps and so on. You see with the Antarctica really, really huge. And Europe in the center is okay. It's a very dangerous map actually. The proportions are really way off. So let's go to the next. Let's go to GeoPandas. I have a dataset cities 5K. That's a dataset CSV file containing all cities with more than 5,000 people living in it. It's also some eras. It's not only cities, it's just populated places actually. So it's UTF-8 encoded with a comma, and it has no header. And to avoid warnings, I use the low memory. This is just pandas, standard pandas, and you see if I display the first three, we see a really horrible data set with many not number and things. I remove some columns now for the demo. I just use the name, latitude, longitude, also the type, so I can remove some things later, and the population. You see the 5K is not really that strict, so it's not really the best data set. It comes from geonames.org. You can download it. It's an open data set, and it contains really many cities and its population. So I remove sections from the data set, some areas which are not interesting for us, and so we only have the most important data set inside. So next I create a GeoPandas data frame. I told before, GeoPandas is basically the same like pandas, but it has a geometry column inside. And this geometry column contains a shapely object. So let me zip this, let me take the longitude, latitude, create a shapely column and create a geodata frame out of it. And you see there is a geometry column now, and with the well-known text here. So we have points mainly. I removed the latitude, longitude from the data set. We don't need it anymore, it's redundant. And I can just take this geodata frame and plot it. Color green, marker size 15. And if I plot it, you see all cities on the world with a marker 15, and you see some areas are really dense and some are not really dense. So you see the shape of the Earth just with cities. So let's take this our location again as example and create a column with distance. So I want to make every city in this world the distance from this place here, exactly this place. And let me display it how it looks. That's a GeoSeries dist. It's just for every row in the data set, it's the distance in degree. Be careful, it's degree, we are in geographic coordinates. And I can create a new row, I call it distance. I copy this geodata frame and add a new row inside, a new column inside called distance, and sort them ascending through, and let me display it. And here we see the distance from here to the next cities. Of course, the next city is Vilnius, because we are in Vilnius. And then don't ask me to pronounce. But probably you know that, and I guess it's correct, or any objections? Okay. So that's the first 10. And I can create a mask now. A suburb is inside too. It's not only city. It's some districts can be inside too in this data set. You could filter it out by using the type. You see here it's PPLA2. There is a whole documentation what is what, and you could filter that too. Okay. So we remember our Lithuania polygon, this really horrible polygon with only a few points. So what I can do is I can create a mask with this. I check if all the cities are within Lithuania polygon and create a new data frame. I also do a little trick here. I just want all places with more than 20,000 people. So it's not too many, so we can see that's all inside Lithuania. Not really inside Lithuania, it's actually inside this simplified polygon. So it could be that a neighbor city is inside here too. Okay, I can use folium now. I can do a combination. I can say, okay, let me create markers inside this. I just create a map, and I use the pandas command apply that just calls a function. And for every row, axis 1, and I can create markers out of it. So with these few lines of code, I can just display all these cities from before on this map. And I also made, in every marker, I used the F string with name, population. So I can click on such a marker and see population and name of the city. Okay, how much time do I have? Okay.
We're wrapping up at 1:30, I think.
So I hurry up. I do one more demo. I want to show some live data. The USGS has a nice web service with earthquakes. It's updated every minute, so that's really more or less live. I can get all the earthquakes with magnitude higher than 2.5. I use this one dataset because there are really many small earthquakes. So let me say I just take the 2.5 ones from the last week up to now and download that. Just here is the URL. You get a GeoJSON, and I just download it here as earthquake.geojson. I write it binary because it's UTF-8. I could do it otherwise. And then I read it, just downloaded here. I read it with GeoPandas directly. I can open it. And you see here we have some IDs, magnitude, oh, that's a big one, and link and time stamp. I also do something magic. I just reduce it to the most important parts: timestamp, magnitude, place, and geometry. And let me do a histogram quickly. That's basic pandas too. And we see there is one really big one. This must be new. I didn't see it when I tested it this morning.
It happened now. It happened now.
Okay, that's really, it's horrible. Yeah, 80s. Okay, so I can convert the timestamp with the time zone. So let's look when it was in UTC. Let me plot it first. We see if we plot this data set, it's not really nice. So what I can do is I can read another shapefile. Shapefile I mentioned before is a standard for vector data, and I can read that and I can plot both. I just saved axis object from the countries I just created and plot the earthquakes on it. and we see, I think it's visible on the projector, yeah, here, the earthquakes from the last week. I could create different size of markers for different magnitudes. That would be a little bit longer code, so you would have to plot for every magnitude. That I didn't do that now, and it's actually usually a exercise for the students to do that. So I don't have it in my standard Jupyter Notebook. I don't want to show it because it's recorded. I could see the solution, so no. So we see this one 741 UTC 0. This was the 75 kilometers from Peru, 8.0. These numbers are not really correct. It could be less. So it's because it's new and it's a complicated thing, but it seems really a really strong earthquake that took place. Okay, so I think my time is up. I didn't show everything, but you can try it yourself. You have the link to the notebook. Thank you for attending, and I'm here for questions.